Welcome to the Explainer. Today, we're going to tackle something that seems, well, totally random. We're diving into the world of probability to see how something like a coin flip can be turned into something we can actually measure, analyze, and even predict.
So here's the big question, right? How do we take these random, real-world events and translate them into the clean, predictable language of mathematics? How do we find the pattern that's hiding in the chaos?
Okay, here's how we're going to break it down. First, we'll see how to convert chance into numbers. Then, we'll get to know the random variable and its two different types. After that, we'll actually build a probability distribution and wrap up with the two simple rules that make the whole thing work.
All right, let's jump right in. Section 1, from chance to numbers. Before we can calculate anything at all, we've got to have a system for turning what happens out there, in the real world, into something we can actually put into an equation. So, in the world of statistics, when we talk about an experiment, we're not just talking about lab coats and beakers. An experiment is literally any repeatable action. Tossing a coin, that's an experiment. Rolling a die, experiment. The different results you can get, heads, tails, a 4, a 6, those are your outcomes. And if you list out every single possible outcome, boom, that's your sample space.
Okay, so we've got our basic language down. Now let's meet the real hero of this story, the tool that makes all this math possible. I'm talking about the random variable.
So what is this thing? Honestly, the best way to think about it is as a translator. Its one and only job is to look at the outcomes of our experiment, things like heads or tails, and assign a specific number to each one. It's the bridge that connects the messy real world to the clean world of numbers.
Okay, let's see this translator in action. Let's say we toss 3 coins. On the left, you see every possible thing that can happen, 8 different outcomes. Now look to the right. Our random variable, we'll just call it x, has gone through and given each one a number based on how many heads there are. So 3 heads, HHH, becomes the number 3. 2 heads, like HHT, becomes 2. And if you get all tails, TTT becomes a big fat 0. See? It's just a simple, clean translation.
And here's the key takeaway from that last slide. After our translator did its job, the only possible values our random variable x can even have are 0, 1, 2, or 3. That's it. It can't be 2.5, it can't be 10. We've taken all that randomness and boiled it down to a very specific, defined set of numbers to work with.
But wait, there's more. It turns out this translator of ours isn't just a one-trick pony. Random variables actually come in 2 distinct flavors, and it all depends on what kind of numbers they're dealing with.
So you've got your discrete variables and your continuous variables. Think of it like this. Discrete is anything you can count, like the number of defective phones in a shipment or the number of dots on a pair of dice. There are clear gaps, right? You can have 2 bad phones or 3, but you can't have 2.5. Continuous variables, on the other hand, are for things you measure, like weight or height or time, where the value can be anything within a range.
Okay, so we've met our random variable. Now let's use it to build something really, really powerful. It's called a probability distribution, and you can think of it as the complete blueprint for our random event.
And it's pretty much exactly what it sounds like. It's just a list or a table that shows you every possible value our random variable can take, and right next to it, the exact probability of it happening. It's like the ultimate cheat sheet for our random event.
So how do you actually make one of these? It's a really simple 4-step recipe. Let's use an example of testing 3 keyboards. Step 1, list out every possible outcome. Step 2, assign a number to each outcome based on how many defects there are. Step 3, group all the outcomes that have the same number. And finally, Step 4, calculate the probability for each of those numbers. Easy.
And voila! Here is our finished blueprint, the probability distribution for our keyboard test. You can see it clear as day. There's a 1 in 8 chance of finding 0 defects. There's a 3 in 8 chance for 1 defect. Same for 2 defects. And another 1 in 8 chance that all 3 are duds. This table tells us everything we need to know about the chances.
Okay, we're almost there. But for this blueprint to be legit, for it to be mathematically sound and actually useful, it has to follow 2 super simple but absolutely non-negotiable rules.
First up, rule number 1. It's just common sense, really. Every single probability on that list has to be a number between 0 and 1, inclusive. You can't have a negative chance of something happening, and you can't have a 150% chance. It's got to be between 0% and 100%.
And rule number 2 is just as crucial. If you add up the probabilities of every single possible outcome, the grand total
has to be exactly 1, 100%. This is how you know you haven't missed anything. It guarantees you've covered all your bases.
So who cares about these rules? Well, we care, because these two properties are our safety net. They're the guarantee that our mathematical model of this random event is solid, it's complete, and it actually lines up with reality.
So think about what we just did. We took something random, defined it, assigned it numbers, and built a whole blueprint that tells us its probabilities. We've basically created a framework to quantify uncertainty. And that leaves us with a final thought. Now that you see how you can map out the chances of a simple coin toss, what other uncertainties in your world could you start to measure and maybe understand a little better?